Most people think about survival the wrong way. They stockpile canned goods that run out and build systems that break. True independence requires systems that operate for decades without external resources. There are 8 systems that can provide food, water, and energy to any family for generations to come. These technologies have been used for centuries, but the modern world has forgotten about them. The most powerful of them produces protein from garbage and expands on its own. Another has been pumping water uphill without electricity for 200 years in a row. The third heats the house all day long with just one kindling in the morning. The total cost of all 8 systems is less than the price of a used car. But they give you complete independence from stores, electricity, and the state forever. When the Soviet Union collapsed in 1991, store shelves emptied within days. People who had relied on the government supply system their whole lives were suddenly left without basic necessities. Only those who had their own sources of food and resources survived. Modern survival systems repeat the same mistake of dependence on external supplies. The chickens need the grain that the trucks bring in. Vegetable gardens require seeds, fertilizers, and fuel for machinery. Solar panels depend on batteries, which fail after 5 years. True autonomy means systems that maintain and expand themselves without external resources. Permaculture founder Bill Mollison defined the principle of self-sustaining ecosystems back in 1978. His work showed that nature creates abundance without fertilizers, pesticides, or constant human intervention. History has proven the power of autonomous systems during crises. When global supply chains were disrupted in 2020, families with their own sources of food and water saw no shortages. They continued to live normally while others stood in line for food. The following 8 systems operate precisely on the principle of complete independence from the outside world. They turn waste into resources, use free natural forces, and expand on their own. The first of them produces the highest quality protein from what others throw away. Traditional livestock farming works like a pump in reverse. You put in 10 calories of feed to get 1 calorie of meat. Every day, chickens need grain, cows need hay, and pigs need feed. Stop supplies for a week, and animals will start to die. Permanent protein systems work in the opposite way. They convert waste into high-quality protein, reproduce on their own, and become more productive every year. Instead of consuming resources, they create them. Dr. Paul Stamets, a leading mycologist of our time, has dedicated his career to studying fungal networks that can produce protein more efficiently than any animal. His research, published in the journal Mycology, showed that mycelium grows faster than muscle tissue and contains all the essential amino acids. The smartest farmers have already understood the secret. Instead of buying feed, they grow feed from their own waste. Earthworms transform kitchen scraps into premium protein for poultry. Mushrooms grow on sawdust, which sawmills give away for free. These systems don't just save money today, they create abundance for decades to come, becoming more productive as they age. As animal agriculture requires more and more resources, permanent protein systems require less and less human labor. Most people consider mushrooms a supermarket delicacy for $3 a kilo. In fact, it is the most efficient protein farm on the planet, operating in the shade and feeding on what woodworkers consider trash. One mother mushroom plant can feed a family with protein all year round. Winecap, also known as King Stropharia, aggressively colonizes wood chips and produces 5 to 15 kilograms of mushrooms per square meter annually. These mushrooms contain 15 to 30% protein by dry weight, more than most vegetables and many meats. The genius of the system is that it expands on its own. Plant mycelium once, and it will spread throughout your yard for decades as long as you feed it with free wood chips. Every spring and autumn, add 10 centimeters of fresh sawdust, and the mycelium will increase the production area. The Field and Forest Company sells winecap spores for $20. This amount is enough to create a mother plantation measuring 3 by 2 meters. Within 2 years, it can expand by hundreds of square meters simply by transplanting colonized wood chips to new locations. The yield amazes even experienced farmers. The 3 by 3 meter plantation produces 100 kilograms of mushrooms per year, which equals 50 kilograms of pure protein. This is the equivalent of eating chicken twice a week for a family of 4. But chicken requires constant feed and mushrooms grow on waste. In the 1980s, industrial mushroom farming created the myth that growing mushrooms required sterile laboratories and sophisticated equipment. This is a complete lie, invented to sell expensive systems. Mushrooms grew in forests for millions of years without any sterility. Outdoor cultivation of mushrooms on wood chips is not only simpler than industrial methods, but also much more productive. Natural microflora helps the mycelium, creating a symbiotic relationship that is not possible in a sterile environment. The wine cap was especially selected as the most stable and aggressive species. Cornell University professor Steve Gabriel has spent 20 years studying small farms and has proven that simple wood chip growing systems outperform complex industrial setups. Its small farm program has recorded similar yields with zero energy inputs. The only requirements for success are shade, moisture, and hardwood wood chips. No special skills, thermometers, or sterilization. You literally pour the spores into a pile of sawdust, water it, and expect a harvest 4 months later. The industry hides the main secret. Mushrooms grow better in nature than in artificial conditions. They evolved to decompose wood in the forest, not to live in plastic containers under fluorescent lights. One wine cap plantation, measuring 3 by 3 meters, produces up to 100 kilograms of fresh mushrooms per season. With mushrooms costing $3 per kilogram, that's $300 in income from a plot the size of a garage. But the main value is not in money, but in protein and independence from stores. Scaling occurs at almost no cost. Each spring you take handfuls of colonized wood chips from the mother plantation and replant them in new locations under trees, along paths, in any shady areas. In 2 years, one plantation can create dozens of new centers of production. Research from the Rodale Institute has shown the incredible effectiveness of mushroom systems compared to traditional farming. In the same area, mushrooms produce 10 times more protein than soybeans and 20 times more than wheat. At the same time, they improve the soil rather than deplete it. A family from Vermont started with one $30 plantation in 2010. Within 10 years, they had expanded production to half a hectare using only mycelium transplants and free wood chips. Now their mushrooms provide protein not only for their family, but also for 10 neighboring families. The most striking thing is that the system becomes more productive with age. A young mycelium produces a modest harvest, but a mature mycelial network that has developed over 5 to 7 years can produce 200 to 300 kilograms of mushrooms from the same area. This is a protein farm that improves on itself. The USDA database contains shocking information about mushrooms. They contain all 9 essential amino acids in proportions similar to meat. At the same time, wine cap is superior to beef in the content of lysine and tryptophan, which are critically important for the human body. Mushrooms contain a unique compound, ergothioneine, a powerful antioxidant that the human body cannot synthesize on its own. Research has linked regular consumption of ergothioneine to a 30 to 40% reduction in the risk of heart disease and cancer. Outdoor-grown mushrooms contain vitamin D in concentrations comparable to fish oil. Ultraviolet radiation converts the ergosterol in mushrooms into vitamin D2, which is absorbed by humans as efficiently as the vitamin from animal sources. The protein content in dried mushrooms reaches 30 to 40%, which exceeds that of most legumes. 100 kilograms of fresh mushrooms yield 15 to 20 kilograms of dry product with concentrated protein, which can be stored for years without refrigeration. Japanese studies of Okinawa centenarians have revealed a direct link between the consumption of a variety of mushrooms and life expectancy. Mushrooms not only replace meat in nutritional value, they surpass it in the content of biologically active compounds that support the immune system and slow down aging. Choose a place in the shade of trees or on the north side of buildings, where direct sunlight reaches no more than 2 to 3 hours a day. The bonnet prefers diffused light and constant humidity, like in a natural forest. Place cardboard on the ground 2 by 4 meters to suppress weeds. The cardboard will decompose within 6 months, but by then, the mycelium will have already colonized the soil. Place a layer of hardwood chips 20 to 30 centimeters thick on top of the cardboard. Order wine cap spores from Fungi Perfecti for $25, or find a Russian supplier of mycelium on grain. 1 kilogram of inoculum is enough for 10 square meters of plantation. Mix the spores with the wood chips in layers like lasagna. Water thoroughly until the sponge is wrung out. The wood chips should be damp but not wet. Cover with burlap or straw to retain moisture and prevent drying out. The total cost of materials will not exceed $40. After 4 to 8 weeks, white threads of mycelium will appear under the straw looking like a spider's web. This means successful colonization. The first mushrooms will appear 4 to 6 months after planting, usually after rain or heavy watering in cool weather. An invisible revolution is taking place underground. 1 cubic centimeter of healthy mushroom soil contains up to several kilometers of mushroom threads, several microns thick. This network grows at a rate of up to 40 centimeters per day, creating an underground web that connects the entire ecosystem. For the first 4 weeks, the mycelium establishes territory by secreting enzymes to decompose wood and suppress competing microorganisms. By the 8th week, the white threads become visible to the naked eye. By the 16th week, the entire pile of wood chips is riddled with mycelium. The first fruiting occurs in the 4th to 6th month, usually in autumn or spring, at temperatures from 10 to 24 degrees and high humidity. The mushrooms appear in groups of 20 to 40, grow for 3 to 5 days, and are ready for harvest. System expansion requires minimal effort. Every spring and fall, add 10 to 15 centimeters of fresh wood chips on top of the old ones. The mycelium quickly colonizes new material, increasing the fruiting area and overall productivity of the plantation. To create new plantations, take handfuls of colonized wood chips from the center of the mother plantation and move them to new locations. Each such transplant can create a new plantation measuring several square meters in one season. The soil under mature mushroom plantations contained 4 times more carbon and 6 times more beneficial microorganisms than regular garden soil. Mushrooms literally create fertility out of waste. The mycelium secretes more than 240 different enzymes that break down wood into humus. This process occurs slowly and evenly, creating a stable soil structure that retains moisture 10 times more efficiently than regular soil. Fungal systems work as natural pharmacists for plants. The mycelium produces antibiotics that suppress pathogenic bacteria and fungi in the soil. Trees and shrubs near mushroom plantations get sick much less often and grow faster thanks to this protection. The carbon cycle in fungal systems works in the opposite direction compared to conventional farming. Instead of releasing carbon dioxide as organic matter decomposes, mycelium sequesters carbon into stable soil compounds that last for decades. This turns your mushroom farm into a carbon sink. Earthworms massively colonize areas under mushroom plantations, attracted by rich organic matter. Their activity further improves the soil structure, creating ideal conditions for the roots of trees and shrubs within a radius of several meters from the mycelium. While the wine cap colonizes wood chips on the ground, vertical space remains unused. Shiitake on logs solves this problem by turning each felled tree into a perennial mushroom farm. One log with a diameter of 20 centimeters will bear fruit for 8 years in a row. Freshly cut oak, maple, or birch logs, 1.5 meters long, become ideal incubators for shiitake. Unlike the fast-growing wine cap, shiitake slowly and methodically decomposes its wood-producing dense fleshy mushrooms with intense flavor. The technology requires a drill and wooden plugs with shiitake mycelium. Drill holes 4 centimeters deep, every 15 centimeters in a checkerboard pattern across the entire surface of the log. Hammer the plugs in and seal with wax to protect against competing microorganisms. The cost of inoculating one log is $3 to $5 per 100 wood plugs with mycelium. One medium-sized log requires 80 to 120 plugs. Sealing wax adds another $1 or $2 to the total cost. The advantage of shiitake is the predictability and duration of fruiting. After 18 months of colonization, the logs begin to produce crops 2 to 3 times a year, 5 to 10 kilograms of mushrooms per log. This system works in parallel with the wine cap doubling the overall protein production. The Ming Dynasty first documented the cultivation of shiitake on logs in 1209, almost 800 years ago. Japanese farmers perfected this technology and passed it down from generation to generation as a family tradition more valuable than land. The village of Takayama in Gifu Prefecture has been producing shiitake continuously since the 14th century. Local families use the same log inoculation techniques as their ancestors did 700 years ago. Some logs are inherited and bear fruit for decades. In the 1940s, when American bombing destroyed Japanese cities, rural families survived on shiitake. Mushrooms provided protein when rice and meat disappeared from the diet. This technology saved thousands of lives during the most difficult years of the war. Modern Japan produces 200,000 tons of shiitake annually, and 70% of this volume is grown on logs in the traditional way rather than in industrial greenhouses. The Japanese understand the superiority of the ancient method over modern technology. Japanese longevity is partly attributed to the regular consumption of shiitake, which is rich in lentenon, a compound that stimulates the immune system. Research shows that people who regularly consume shiitake live an average of 7 years longer and are less likely to get cancer. Mushrooms solve the protein problem, but survival requires water first. Most autonomous systems depend on electricity, well pumps, filters, water supply systems. When the power goes out, these systems turn into expensive scrap metal in a matter of hours. The hydraulic ram works on the principle that was discovered by Joseph Michel Montgolfier in 1796. The energy of falling water creates hydraulic shocks, which raise part of the water to a height of up to 300 meters without any fuel or electricity. This technology powered the water supplies of European cities before the advent of electricity. In London, hydraulic rams pumped water from the Thames onto the city's towers until 1920. Some of these installations operated continuously for more than 100 years without major repairs. A modern hydraulic ram the size of a microwave oven can lift 1,000 liters of water a day to a height of 100 meters using a flow of only 20 liters per minute. This means an efficiency of 10 to 15%. But who cares about efficiency when the system has been running for free around the clock for decades? The only requirements, a source of running water and a height difference of at least 1 meter for every 10 meters of ascent. If you have a stream or a spring uphill from your home, a hydraulic ram will solve the water problem for good. An elegant play of physical forces takes place inside the hydraulic ram. Water flows down the pipe, picking up speed under the influence of gravity. When the flow reaches a critical speed, a special valve abruptly stops the movement of water, creating a hydraulic shock of enormous force. This impact lasts a fraction of a second, but creates a pressure 10 to 20 times higher than the static pressure of the water in the pipe. Excessive pressure opens the check valve and pushes a portion of water into the pressure chamber from where it rises through the outlet pipe up to the consumer. After the impact, the pressure drops, the check valve closes, and the rebound valve opens again for the next cycle. The entire process is repeated 30 to 60 times per minute, creating a characteristic rhythmic knocking sound that can be heard hundreds of meters away. Hydraulic studies show that the effectiveness of a ram depends on the ratio of the lifting height to the falling height. When climbing 10 meters with a fall of 1 meter, the efficiency is 15%. When climbing 100 meters with a fall of 10 meters, the efficiency is reduced to 5%. The beauty of the system is that the lost water is not wasted. It is returned to the same stream downstream. The ram uses excess water in the source to lift the required part to the top. It is a closed ecological system without waste or side effects. The Anderson family from Vermont installed a Rife hydraulic ram in 1980 on a mountain stream with a drop of 4 meters. Over 43 years of operation, the system supplied more than 5 million liters of water to a house located 80 meters above the source. Their ram operates with a capacity of 1,200 liters per day, which covers the needs of a family of 6 people with a reserve for watering the garden. Repairs were required only twice: replacement of the leather valves after 15 years and after 30 years of operation at a cost of $30 per set. A monastery in the Swiss Alps uses a hydraulic ram installed in 1892. This system has continuously supplied water for 131 years, surviving 2 world wars and many generations of monks. The original cast iron parts are still functional. Compare this to electric well pumps, which break down every 7 to 10 years and cost between $80 and $150 to install. Over a 40-year period, an electric pump will require 4 to 5 replacements at a total cost of $5,000 plus electric bills. In winter, the hydraulic ram continues to operate until the stream freezes completely. In regions with mild winters, the system operates year-round. At temperatures below -20 degrees, the housing must be insulated or installed in a frost-free place. A successful installation begins with choosing the right location. Measure the water flow at the source during the driest period of the year. This will determine the maximum performance of the system. A hydraulic ram requires a minimum of 20 liters per minute of constant flow for stable operation. Lay a pressure pipe with a diameter of 50 millimeters from the source to the installation site of the ram with a constant slope without horizontal sections. Every turn and bump reduces efficiency by 10 to 15%. Use HDPE pipes that can withstand water hammer. Place the battering ram on a concrete base at the lowest point of the system. The housing must be accessible for maintenance, but protected from freezing. Many owners build a small insulated house around the ram for year-round use in cold climates. A supply pipe with a diameter of 25 millimeters runs from the ram to a storage tank with a volume of at least 1,000 liters. The tank is installed at the highest point of the system and ensures a uniform supply of water even when the ram is temporarily stopped for maintenance. Setting up the system takes several hours of experimenting with valve adjustments. A properly tuned ram produces an even rhythmic knock without skipping or jerking. The sound becomes music to the owner, a sign that water is rising into the house without his participation. Failure statistics for electric well pumps show an average operating time of 7,000 hours, which is equal to 3 to 4 years with constant operation. The main causes of breakdowns: burnt-out motor windings, wear of bearings, clogged filters, and power surges. Replacing a deep well pump requires special equipment to lift it out of the well. The cost of the work is $200 to $300 plus the price of new equipment. Many owners wait for repairmen for weeks, remaining without water at the most critical moments. A hydraulic ram contains only 2 moving parts: a breaker valve and a check valve. Both are made from bronze or stainless steel and last for decades. The only consumables are leather pads, which cost $5 a set. Maintenance of the ram is carried out by the owner in 30 minutes without special tools. Open the housing, inspect the valves, remove sand and debris, and replace gaskets if necessary. No electricians, plumbers, or cranes. Electrical systems depend on a stable power supply, which is becoming increasingly unreliable. Power outages, power surges, and accidents at substations leave modern homes without water. The hydraulic ram works independently of civilization as long as the stream flows. Not everywhere there are mountain streams for hydraulic rams, but groundwater is available almost everywhere at a depth of 5 to 25 meters. A hand pump turns any point with groundwater into an independent source of water supply without electricity and fuel forever. Modern hand pumps have come a long way from the primitive pumps of the Soviet era. The Bison Pump Company produces systems capable of delivering 10 to 15 liters per minute from a depth of 20 meters with moderate physical effort by an adult. Performance amazes skeptics. An adult man working at a comfortable pace delivers 600 liters per hour. To provide a family of 4 with a daily requirement of 200 liters, it takes only 20 minutes of work divided among family members. Physical laws limit the operation of piston pumps to a depth of 25 meters due to atmospheric pressure. At greater depths, vacuum cannot lift water higher. But for most areas, this is enough. Statistics show that 70% of the Russian territory has groundwater in this range. Installation is possible in an existing well in parallel with an electric pump. This creates a backup system that operates during a power outage. Many owners find that a hand pump is so convenient that they stop using an electric one. Settlers of the American West in the 1860s and 1970s built farms entirely on hand pumps, providing water for families of 8 to 10 people plus livestock. Pioneer diaries record consumption of 200 to 300 liters per person per day, including household needs, washing, and cooking. The Ingalls family, made famous by the books of Laura Ingalls Wilder, lived on the South Dakota prairies using a hand pump as their only source of water. Their 18-meter deep well provided water for a family of 6, a half-hectare garden, and livestock for 30 years. Modern ergonomic research has shown the optimal technique for working with a hand pump. Moving your whole body instead of working only with your hands doubles your productivity and reduces fatigue. With the right technique, you can pump water for an hour straight without undue strain. Comparison with modern needs shows the feasibility of manual water supply. The average Russian family consumes 200 to 300 liters of water per day, including showering, laundry, washing dishes, and cooking. This corresponds to 40 minutes of pump operation distributed among all family members. The quality of water from shallow wells is often superior to tap water due to natural filtration through the soil. Groundwater contains less chemical contaminants and chlorine, but may require testing for bacterial contamination, especially near septic tanks and farms. A driven well is a steel pipe with a diameter of 50 millimeters with a mesh filter at the end, which is driven into the ground down to the aquifer. This technology allows you to get water in one day of work in sandy and sandy loam soils without drilling or heavy equipment. A drive well kit costs $80 to $120 and includes steel pipes with threaded connections, a pointed tip with a filter, a drive headstock, and a hand pump. The entire process only requires a sledgehammer, pipe wrenches, and 2 people to operate. Driving occurs in stages. Connect the first pipe to the tip, drive it to a depth of 3 meters, check for water, and if necessary, add the next section. The process continues until the aquifer is reached, which usually occurs at a depth of 5 to 15 meters in suitable soils. Sign of reaching water, a sharp increase in driving speed, and the appearance of wet sand on the surface around the pipe. After this, install a hand pump and pump the well for an hour to remove turbid water and stabilize the flow rate. Limitations of the method: does not work in rocky and clay soils, requires a close location of the aquifer. The flow rate is lower than that of drilled wells. But the advantages are obvious: minimal cost, quick installation, the ability to do it yourself without specialists or equipment. Atmospheric pressure creates an insurmountable barrier at a height of 10.5 meters above the water level. Regardless of the strength of man or the perfection of the pump, this is a physical law that cannot be circumvented by piston systems. In practice, the limit is 8 to 9 meters due to friction losses and system leaks. For deep wells, there are rod pumps that operate on the principle of a lever with a system of rods that transmit force to a deep piston. The Simple Pump Company produces systems for depths of up to 100 meters, but the physical effort increases in proportion to the depth. A rod pump for a depth of 50 meters requires the effort of an adult man to supply 3 to 4 liters per minute. This means an hour of work to obtain 200 liters of water. The system is functional, but requires significant physical effort and costs $400 to $600. An alternative approach for deep wells is a windmill, which automatically pumps water when winds exceed 3 meters per second. American ranches have been using wind pumps since the 1870s to water livestock on pastures where there is no electricity. The combination system combines a hand pump for daily needs and a windmill for filling storage tanks. The wind operates free of charge around the clock, and the hand pump ensures independence from weather conditions during calm periods. Modern wood stoves burn wood inefficiently, expelling 80% of the heat down the chimney along with smoke and unburned gases. A stone stove works in the opposite way. It burns wood at a temperature of 2,000 degrees with complete combustion, accumulates all the heat in the stones, and releases it evenly throughout the day. The principle is based on the accumulation of thermal energy in a mass of stone or brick weighing 3 to 6 tons. Hot gases pass through a system of smoke channels inside this mass, transferring almost all of their heat to it before exiting into the chimney. The surface of the oven heats up only to 80 to 100 degrees. Finnish counterflow stoves and Russian hotbeds have been using this principle for centuries. In Finland, stone stoves heat houses at temperatures as low as 30 degrees, requiring only 1 or 2 fires per day. Some Finnish stoves have been operating continuously since the 18th century. Even engineers are amazed by the efficiency. One stack of firewood weighing 20 kilograms heats a house of 100 square meters for 24 hours at a temperature outside the window of minus 20 degrees. An ordinary iron stove will burn 80 kilograms of wood for the same result. When fuel becomes a scarce resource, the stone stove will become a means of survival. A 4-fold saving of firewood means that instead of preparing 10 cubic meters for the winter, 2.5 cubic meters are enough. It's the difference between surviving and freezing. An ordinary iron stove operates at a combustion temperature of 600 to 800 degrees, which is not enough to completely burn wood gases. The smoke coming out of the chimney contains unburned hydrocarbons that could provide additional heat. It's like throwing a third of the firewood out the window. A stone stove creates a combustion temperature of up to 2,000 degrees in a fireproof chamber, where wood gases burn completely. The smoke at the outlet is transparent. The temperature of the exhaust gases is only 100 to 150 degrees instead of 300 to 400 for iron stoves. This means extracting maximum energy from each log. Emission studies show that masonry stoves produce 10 times less particulate matter and carbon monoxide than conventional wood stoves. Complete combustion at high temperatures eliminates most harmful substances, making stone stoves environmentally friendly. The combustion mode is radically different from the usual one. Instead of keeping the fire going all day, you load up 20 to 40 kilograms of dry wood and burn it in 1.5 to 2 hours at maximum intensity. The oven then releases the accumulated heat for the next 22 hours. Savings become obvious already in the first winter. A family from Karelia reduced their firewood consumption from 12 to 3 cubic meters per year after replacing their iron stove with a stone one. With the cost of firewood being $30 per cubic meter, the savings amounted to $270 annually. Building a masonry oven requires an understanding of the movement of hot gases and heat transfer, but not extraordinary skill. The basis for success is the correct design of the firebox made of refractory bricks and the smoke channel system, which forces the gases to give off maximum heat before venting outside. Modern plans from the Masonry Heater Association provide detailed drawings and step-by-step instructions for DIY construction. Materials cost $1,000 to $1,500. Fire-resistant brick for the firebox. Ordinary brick for the mass. Clay mortar. Stainless steel chimney. Professional construction will cost $3,000 to $5,000, but the result will last for centuries. The stone stoves in the castles of Europe last 500 to 600 years with periodic repairs to the combustion chamber every 30 to 40 years at a cost of $200 to $300. The key element is a fireproof firebox that can withstand temperatures over 2,000 degrees. Use only fire clay bricks of the Schach or SHB brand and clay mortar without cement. The cement mortar cracks due to high temperatures and destroys the structure within a few years. The mass of the furnace determines the duration of heat transfer. 3 tons of brick accumulate heat for 12 to 15 hours, 6 tons for 24 hours. The greater weight requires a reinforced foundation, but provides more uniform heating and requires less combustion. Most people think of preserving their crops through canning, freezing, or drying. A root cellar is simpler and more efficient. It maintains temperatures between 0 and 4 degrees and humidity of 85 to 95%, creating ideal conditions for storing fresh vegetables for months. 100 kilograms of potatoes harvested in October remain fresh until May of the following year. Carrots, beets, and turnips are stored all winter without loss of taste and nutrients. Cabbage lasts until March. Winter apples until April. This is a natural refrigerator without electricity. The University of Minnesota conducted research into the optimal storage conditions for root vegetables and established precise parameters for maximum shelf life. Potatoes require a temperature of 2 to 4 degrees and a humidity of 90 to 95%. Apples are stored at 0 to 2 degrees and 85 to 90% humidity. The volume of the root cellar, measuring 3 by 4 meters, can accommodate 500 to 1,000 kilograms of vegetables. This is a 3 to 6 month supply of vegetables for a family of 4, housed in a space the size of a small room underground. The Amish have used root cellars for 300 years and consider them superior to modern refrigeration for long-term vegetable storage. Many root cellars in Pennsylvania have operated continuously since the 18th century, providing families with fresh vegetables every winter. A properly constructed root cellar turns fall harvests into year-round nutrition. 1,000 kilograms of a variety of vegetables takes up only 8 to 10 cubic meters of space when properly placed in boxes, on shelves, and in sandbags. Different vegetables require specific conditions, but most root vegetables work well together. Potatoes, carrots, beets, rutabaga, parsnips are stored at the same temperature and humidity. Onions require drier conditions, so they are placed on the upper shelves where the humidity is lower. Apples emit ethylene gas, which speeds up the ripening of other fruits and vegetables, so they are stored separately in ventilated boxes. Winter varieties of apples, such as Antonovka or Northern Sinap, last to 6 months if the temperature conditions are observed. Cabbage is stored in a special way. Heads of cabbage with roots are hung from the ceiling or stacked, interspersed with straw. At temperatures around freezing, cabbage stays fresh for up to 5 months, providing vitamins during the harshest winter months. Losses with proper storage amount to 5 to 10%, which is incomparably better than modern vegetable storage facilities with losses of 20 to 30%. The natural environment of a root cellar supports the life processes of vegetables, keeping them fresh much longer than artificial refrigeration. Building a root cellar begins with choosing an elevated location with good drainage. Dig into the hillside to a depth of 2 to 2.5 meters, where the soil provides natural insulation and stable temperatures all year round. Lay out the walls from cinder blocks or fill them with concrete 20 centimeters thick to protect them from freezing and maintain structural strength. Make the floor from compacted gravel with sand. This provides drainage and maintains the necessary humidity. The ceiling requires special attention to insulation. Cover the wooden beams with boards, then with roofing felt, and cover with a layer of earth 1.5 meters. This mass of earth creates thermal inertia, preventing temperature fluctuations as the weather above changes. The ventilation system is critical and works on the principles of natural convection. Install 2 pipes with a diameter of 10 centimeters, a supply pipe near the floor to supply cold air, and an exhaust pipe near the ceiling to remove warm, humid air. The supply pipe ends at the floor and sucks in cold outside air. The exhaust pipe starts from the ceiling and removes the heated air outside. The temperature difference creates constant circulation without fans, maintaining optimal conditions automatically. Most people think of composting as a way to dispose of waste. Worm farming turns kitchen scraps into high-quality protein that can feed poultry, fish, or even humans in extreme situations. This is a living protein factory running on garbage. California redworms reproduce at an astonishing rate. The population doubles every 60 to 90 days under optimal conditions. Starting with 1 kilogram of worms for $20, after 9 months, you will get 8 kilograms of live protein. Research from the University of North Carolina has shown the incredible effectiveness of worms in recycling organic waste. 1 kilogram of worms processes 1.5 kilograms of food waste daily, turning them into valuable vermicompost and an increase in worm mass. The protein value of worms surpasses many traditional sources. Worms contain 25% protein in their raw form and all the essential amino acids in the correct proportions. In terms of amino acid composition, they are close to fish meal, a premium feed in livestock farming. 6. Laying hens fed worms as a protein supplement maintain egg production with 50% less commercial feed. You create premium protein from waste while reducing feed costs and recycling kitchen waste. One adult worm lays 2 to 3 cocoons per week, each containing 3 to 4 young worms. At a temperature of 20 to 25 degrees, young animals reach sexual maturity in 2 months and begin their own reproduction. The mathematics of reproduction is amazing. 1,000 worms turn into 16,000 in 6 months. The population density is regulated by the volume of the container and the amount of food. In a standard 50-liter container, 2 to 3 kilograms of worms live comfortably, consuming 3 to 4 kilograms of food waste weekly. This corresponds to the waste of a family of 4 to 5 people. The yield of pure protein impresses even skeptics. 3 kilograms of worms contain 750 grams of pure protein, the equivalent of 3 kilograms of chicken meat. The difference is that chickens require constant feeding of grain, while worms grow on waste that is usually thrown away. Harvesting occurs by migration. Prepare fresh bedding with food in one part of the container. In 2 weeks, the worms will crawl to new food, leaving ready-made vermicompost and a concentrated population for collection. Half of the worms can be collected to feed birds or expand the system. The annual production of a mature worm farm is 15 to 20 kilograms of live worms from an initial population of 1 kilogram. This is the protein equivalent of 80 kilograms of chicken produced from kitchen waste without external feed costs. The worm farming system fits in the kitchen and requires minimal effort. Buy 3 18-liter plastic containers for $4 each. Drill holes with a diameter of 5 millimeters every 10 centimeters in the walls and lid for ventilation. Drill drainage holes in the bottom of the work container to drain excess moisture. Insert the working container into the drainage container to collect liquid, which is valuable fertilizer. Fill a work container 10 centimeters thick with shredded cardboard or coconut fiber. Add 1 kilogram of California redworms for $20 from a trusted supplier. Moisten the litter until it feels like a wrung-out sponge. Bury the first batch of shredded food scraps under the bedding in one corner of the container. Feed the worms weekly by burying waste in different corners of the container one at a time. Avoid citrus fruits, onions, garlic, and meats, which increase acidity and attract pests. Ideal food: vegetable peelings, coffee grounds, tea bags, crushed eggshells. Worms are collected every 2 to 3 months using the light separation method. Pour the contents of the container onto the table under a bright lamp. The worms will move away from the light and into the depths of the pile in 15 minutes. Collect the top layer of finished compost. Repeat the procedure until the worms are concentrated in a small volume. The UN Food Organization recognizes worms as a legitimate source of protein for humans in emergency situations. Worms contain all essential amino acids, B vitamins, and trace elements in concentrations exceeding many traditional foods. Indigenous peoples of Australia have consumed grubs and worms for thousands of years as a major source of protein in arid regions. Aboriginal tribes considered large larvae a delicacy with high nutritional value, superior to kangaroo meat in terms of fat and protein content. Before use, the worms are cleaned by keeping them on clean cornmeal for a day to free the digestive tract from soil and waste. After cleaning, the worms are washed, boiled for 10 minutes to kill possible pathogens, and ground to be added to porridges or soups. The taste of cooked worms is neutral, slightly nutty, without any unpleasant taste or odor. In an extreme situation, 200 grams of worms provide 50 grams of complete protein, the daily requirement of an adult with minimal physical activity. The psychological barrier remains the main obstacle, but hunger quickly changes food preferences. During the siege of Leningrad, people ate everything that contained protein. A worm farm in the kitchen can be the difference between life and death during a prolonged disruption to the food supply. Annual farming requires annual plowing, planting, weeding, watering, and pest control. A food forest works in the opposite way. It mimics a natural forest ecosystem, where edible trees, shrubs, and grasses grow together, supporting each other without human intervention. Robert Hart created the first documented food forest in England in the 1960s on a half-hectare site. For 40 years, this forest produced fruits, nuts, berries, mushrooms, and medicinal herbs, requiring only 20 hours of work each year to harvest. A forest ecosystem exists for millions of years without fertilizers, pesticides, or watering because different plants perform specialized functions. Trees provide shade and protection. Shrubs fix nitrogen. Grasses cover the soil. Fungi decompose organic matter and transport nutrients. A food forest replicates this structure by replacing wild plants with edible counterparts. Walnuts are planted instead of oak. Cultivated ones are planted instead of wild raspberries. And edible perennial vegetables are planted instead of weeds. The result? An edible ecosystem that becomes more productive with age. The World Agroforestry Center has studied hundreds of food forests around the world and confirmed their superiority to annual cropping in yields, drought tolerance, soil carbon storage, and biodiversity. The food forest consists of 7 functional layers, each occupying its own ecological niche and maximizing the use of space. Large trees form a canopy at a height of 10 to 20 meters. Small trees fill the undergrowth. Shrubs form the middle tier, and grasses cover the ground. Nut trees, walnut, hazelnut, chestnut, form the top tier and provide the main calories. One mature walnut produces 50 to 80 kilograms of nuts annually for a century. This is the equivalent of 1,200 kilocalories per square meter of crown projection. Fruit trees, apple trees, pears, plums occupy the middle tier between the nuts. Dwarf rootstocks allow you to fit more trees into a limited area. Apple trees on a dwarf rootstock begin to bear fruit in the 2nd or 3rd year and produce 20 to 40 kilograms of fruit annually. Berry bushes, currants, gooseberries, honeysuckle form the lower tree layer. They are shade-tolerant and bear fruit under the canopy of trees where ordinary vegetables cannot grow. A currant bush produces 3 to 5 kilograms of berries within 15 to 20 years. The ground cover layer consists of perennial vegetables and herbs: rhubarb, asparagus, perennial onions, sorrel, lovage. These plants do not require annual planting and produce crops for decades. The root layer includes Jerusalem artichokes and other edible root vegetables that reproduce themselves. A mature food forest covering an area of 1/4 of a hectare produces 1,000 to 3,000 kilograms of nuts, 500 to 1,500 kilograms of fruit, 200 to 500 kilograms of berries, and hundreds of kilograms of perennial vegetables annually. This is a complete meal for a family of 4 with a surplus for canning and trading. Studies of agroforestry systems in the tropics have shown yields 3 to 5 times higher than traditional farming on the same area. The tiered structure uses solar energy more efficiently than annual crops, which leave much of the space empty. Food forest productivity increases with age, in contrast to depleted annual systems. Young trees produce a modest harvest, but by the 10th year, the system reaches a peak fruiting and maintains it for 50 to 70 years without decline with minimal care. Cost-effectiveness amazes even skeptics. An Oregon family invested $15,000 to create a half-acre food forest in 2005. By 2015, the system was producing $8,000 worth of products annually using 40 hours of labor per year. Tolerance to extreme weather is superior to annual crops due to the tree's deep roots and diversity of species. Drought, late frost, or hail can destroy a vegetable garden, but the food forest continues to produce thanks to the varying maturation times and hardiness of perennials. Nitrogen-fixing plants contain bacteria of the genus Rhizobium in their root nodules, which capture atmospheric nitrogen and convert it into ammonia, which is available for plant nutrition. This process replaces commercial fertilizers with a natural nitrogen factory right in the roots of trees and shrubs. Siberian acacia, silver oleaster, and sea buckthorn are frost-resistant nitrogen fixers that grow well in the Russian climate. The roots of these plants enrich the soil with nitrogen within a radius of several meters, nourishing neighboring fruit trees and increasing their yield by 30 to 50%. Leguminous grasses, clover, alfalfa, sweet clover create a living mulch under trees while fixing nitrogen and suppressing weeds. The cut greens of these plants contain more nitrogen than manure and serve as free fertilizer for the entire system when decomposed. The amount of fixed nitrogen is impressive. A mature Siberian acacia tree fixes 50 to 80 kilograms of nitrogen per year, the equivalent of 300 kilograms of ammonium nitrate worth $150. At the same time, the tree grows for free and works for decades. Pruning nitrogen-fixing shrubs provides double benefits. The cut branches are used as nitrogen-rich mulch, and the roots left in the soil decompose, releasing stored nitrogen to feed other plants. This creates a closed cycle of fertility without external fertilizers. The first year requires maximum effort: planning, purchasing seedlings, preparing the soil, and planting the main trees and shrubs. Costs range from $500 to $800 per quarter hectare. But this is the only major investment in the history of the system. The second and third years are devoted to watering, mulching, and protecting young plants from weeds. The harvest is minimal, but nitrogen-fixing plants begin to enrich the soil. Labor costs amount to 100 to 120 hours annually for watering, weeding, and formative pruning. The fourth and fifth years mark a turning point. Berry bushes begin to bear full fruit. The first apple trees produce a significant harvest. Ground cover perennials grow and suppress weeds. The system already requires 60 to 80 hours of maintenance per year. By the 7th to 10th year, the food forest reaches maturity and begins to maintain itself. Leaf litter creates a natural mulch that suppresses weeds. The developed root system extracts water from the depths, eliminating the need for watering. Beneficial insects control pests. A mature system requires only harvesting, sanitary pruning, and the periodic addition of new plants to replace dead ones. Labor costs are reduced to 20 to 40 hours per year, less than a typical garden of 100 square meters requires, but the yield is 10 times larger. The 8 systems work synergistically, creating complete autonomy from external supplies of food, water, and energy. Mushroom plantations and worm farming provide protein. A food forest provides carbohydrates and vitamins. A root cellar preserves crops for the winter, and a stone stove heats the house efficiently. The water systems, hydraulic ram and hand pumps, operate independently of electricity and supply water to all other systems. Without a reliable water supply, it is impossible to water mushroom plantations, feed worms, or ensure the growth of a food forest during dry periods. Waste from one system becomes resources for another, creating closed cycles without losses. Fallen leaves from the food forest mulch mushroom patches. Kitchen waste feeds worms. Worm compost fertilizes trees. Wood ash from a stone oven deoxidizes the soil. The time cycles of the systems complement each other. While the food forest gains strength for the first 5 years, mushrooms and worms provide ongoing nutrition. Once the trees begin to bear fruit fully, the protein systems go into maintenance mode, requiring minimal attention. The total cost of all 8 systems is $2,000 to $3,000 at a time. This is less than the price of a new car, but creates a lifetime of independence from stores, utilities, and government supply systems for the entire family for generations to come. When civilization fails, these systems will continue to work. When the power goes out, the masonry stove will heat the house. When the stores close, the food forest will feed the family. When the water main breaks, the hydraulic ram will pump water from the stream. This is not survival. This is thriving, regardless of the outside world.